Hello and welcome to Unit 7 Bonding, Lecture B. Today we're going to talk about ionic bonds. Different types of bonds are going to be classified depending on how the interaction between the electrons takes place. The electrons are either going to be actually removed from the atom, and if you take a neutral atom and you remove an electron, you form an ion. And remembering that positive ions are called cations and negative ions are called anions. Those ions then form what we call an ionic bond. The other choice would be to share your electrons, and in that case, the orbitals overlap. We share the electrons, and we call that a covalent bond, and that will be Lecture C's topic. So, ionic bonds first. They're going to try and trade their electrons until they look like noble gases. So, quick review on the periodic table. Noble gases are over here in group 18, and the elements want to look like the noble gases in group 18. So when we look at, for example, fluorine, his electron configuration is 2-7. Well, the closest noble gas is neon. He wants to have an electron configuration of 2-8. He would need to gain one electron, which would make him a -1 ion. If we're over here at sodium square, his electron configuration is 2-8-1. He would either need to gain 7 electrons to look like argon 2-8-8, or go backwards and lose 1 electron so that he also could look like neon 2-8. That's the easier thing to do, so he loses that 1 valence electron and becomes a +1 ion. So they're going to look like the closest noble gas, and if we're talking about ionic bonds, they're going to gain or lose electrons in order to do that. Remembering that metals tend to have low ionization energies and lose their electrons, and nonmetals tend to have high electronegativities and gain electrons. The electrons cannot just disappear. We can't form a positive ion without also forming a negative ion. So if this guy's neutral and he loses this 1 electron, he's going to become a +1 ion. Notice he got smaller. If chlorine is neutral and he gains an electron in that spot, so now here it is, he becomes negative because he has an extra electron. The opposite charges then attract, like charges repel, opposites attract, and we get the sodium positive ions clinging to the negative chlorine ions in this 1-to-1 ratio, so that your overall particle is neutral again. The overall particle we're going to make when we make ionic bonds will also be neutral, and here we have our sodium chloride. Keep in mind that we can make ionic bonds between ions and polyatomic ions. Remember, we had sodium hydroxide, so sodium will be a positively charged ion, but hydroxide is a polyatomic ion, and when we get to covalent bonds, I will talk about how this ion forms, but what you have is a hydrogen covalently bonded to an oxygen. The sodium is a regular ion, +1. The polyatomic ion hydroxide has a charge of -1, and the opposite charges make those two things cling together. So this is the ionic bond. This is going to be our covalent bond. So polyatomic ions are made with covalent bonds, and more on covalent bonds in Lecture C. Properties of ionic solids. So how, when you're looking at a compound, do you know if you have something that's made with ionic bonds? We can look basically really quick. It's generally a metal and a nonmetal. That's going to be your basic clue that you have an ionic compound. If you don't have the formula and you're looking at crystals and you want to know whether it is ionic or covalent, ionic compounds have very high melting points. They do not conduct electricity as solids. Remember, they're neutral particles as solids, in order to conduct electricity, we need some areas of charge. But if we make them aqueous or we melt them, they dissociate. So they're going to break apart into their ions. So if I have neutral sodium chloride and I add it to water, it's going to dissociate into sodium ions and chlorine ions. And the water particles are right here in the aqueous. That's your water. What happens is the particles get surrounded by water. So if we look at the diagram, here we have neutral sodium chloride, doesn't conduct, neutral particle. When we put it in water, water is going to have a positive side, and that's where the hydrogens are, and a negative side, that's where the oxygen is. And the opposite charges are going to surround the ions. So the negative side of the water faces the sodium ions, and the positive side of the water ends up facing the chlorine ions, and the water is strong enough to break them apart. And once they get surrounded, now I have an area of positive charge right here in my sodium. Notice the sodium's positive and my chlorine's negative. So now I have my opposite charges to help push and pull electrons through. This will conduct electricity. So aqueous, ionic, aqueous conducts, ionic solid does not. Make sure you know that because it is a very common question to ask. The ionic compounds are going to be your true solids with crystalline patterns, and the best example and the one they use most often will be sodium chloride. So that's the one that you see given as an example of an ionic compound. We're going to look at a couple of examples of how we draw ionic compounds and their properties, and we're going to start with lithium bromide. So lithium is our metal and bromine is our nonmetal, and if you use your periodic table to look up their electron configurations, lithium over here in group 1 is 2-1, and bromine over here in group 17, 2-8-18-7. So let's try to remember those and put those in. 2-8-18-7. Okay, their oxidation states. Where do you find that? The charge that the ion is going to become. That's also on your periodic table. Lithium is in group 1. He's going to lose this 1 electron. So if he loses the 1 electron, he will become +1, and that's going to make his electron configuration 2, or he's going to look like helium. Bromine is in group 17. That means he needs to gain 1 electron, so this fills up to 8. So his electron configuration will be 2-8-18-8. Remember that we are always gaining or losing those electrons from the outermost energy level, so in his valence energy level. So he's going to look like, that would be helium, neon, argon, should be krypton. So I filled that in the wrong place. He looks like helium, and he looks like krypton. Lewis dot structures. Remember, we start with the element kernel. So the protons, neutrons, and inner electrons are the symbol. That's called the kernel. And then we put the valence electrons on. Lithium only had 1 valence electron. When he becomes the lithium +1 ion, he has no valence electrons. He gets no dots. Bromine is in group 17. So as the bromine atom, he has 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. When he becomes the bromine -1 ion, he has filled his last orbital, and he has 8 valence electrons now. 8 valence electrons, and a -1 charge. The opposite charges attract. When we write this as a compound, the positive ion has no dots and in brackets. The negative ion has 8 dots and in brackets, and then we check the charges. +1, -1, that adds up to 0. This is the Lewis dot structure for the compound lithium bromide. Let's look at another example where the charges aren't going to be exactly the same. So magnesium fluoride, electron configurations on the periodic table, magnesium 282, fluorine 2-7. You see where I'm getting these right? So magnesium 282 and fluorine 2-7. When they're an ion, magnesium's in group 2, he's going to be +2, so he loses 2 electrons, 2-8. That makes him look like neon. So if we look at our periodic table, magnesium loses 2 electrons, he goes back 2 squares to neon. Fluorine is going to gain 1 electron, so he's going to move forward 1 square to also look like neon. So fluorine becomes -1. His electron configuration becomes 2-8 because the 1 electron he gained is added to the valence energy level. He also has an electron configuration like neon. Their Lewis dot diagrams. Magnesium had 2 valence electrons. To become a +2, he loses both of those valence electrons, so he has no dots. Fluorine had 7. 1, 2, 3, 4, 5, 6, 7. When he becomes a -1 ion, he needs to fill his remaining orbital for the electron and becomes -1. When we draw this as a compound, the magnesium has no dots and in brackets. The fluorine has his 8 dots and in brackets. But now my charge is +2 and -1. If magnesium lost 2 electrons and one of them goes to fluorine, where does the second electron go? It has to go to a second fluorine. So you have 2 choices for writing this out. You can write a complete second fluorine, or you can use subscripts. So the way that I typically do it is with the subscript because it's just like forming compounds. If I have +2 and -1, least common multiple is 2. I'm going to need 2 fluorines to use up the 2 electrons given off by magnesium. And so this would be the Lewis dot structure for the compound magnesium fluoride. Lecture C is covalent bonds. That's coming up next.